Hello, guys. Nice to have you here. Um, Welcome to this new webinar. This is, I think, the fourth or fifth webinar, actually. There's going to be more. I just have to organize things for the next weeks because I'm going back to university. Today we are going to talk about loops in Grasshopper. I prepared a quick presentation here for a quick introduction. Actually, what I want to point out here is that there is a special offer for this lockdown, uh, global lockdown that we are living. About this bundle here, which offers 5 Grasshopper courses, video courses, at basically the half the price of one. You can click on the information link here in this window if you are on YouTube, or else you can go and just visit my website, and the video course is available here. Um, Yesterday, I finished recording the last session of the Kangaroo Reloaded. With the last topic was origami structures, but it was quite a very nice course. We covered topics like rigid bodies and beams and tensecurity structures, and finally origami. As you can see, these are some outcomes from the last lesson. These are the webinars that are already available on my YouTube channel. So if you want to take a look and simply view them, they are available for free. And I do recommend that you, especially between these four here, I do recommend absolutely that you take a look at the data trees webinar, because for those who want to work with Grasshopper, this is fundamental. And of course, there is the textile simulation with Kangaroo, which is basically all the first part of any Kangaroo course is basically contains this kind of topics. So it's very important in order to understand how Kangaroo works in general. Um, Tomorrow, I'm going to stream this other webinar, which is on NURBS topology in Rhino. Also, you might know that I wrote a book on this, so it's some kind of an introduction to how to better understand NURBS topology, how it works, and how to take advantage in order to optimize the 3D modeling workflow. And it's going to happen tomorrow at 10 a.m. Mexico time. This is basically something that reminds to a new video course that I'll be giving starting from next week, which is actually the extended version of the webinar that's happening tomorrow. So it's going to be advanced NURBS modeling with Rhino. It's going to be based on my book, which is a method. And we are going to cover several aspects, and the program is available on my website. So if you want, you can check the online training section where you will find the Mastering NURBS Topology video course. And if you are into 3D modeling, I do recommend that you take a look at that video course. And for those who are not following this webinar on YouTube, I remind you that there is my YouTube channel that contains all the tutorials and webinars that I am giving in this period. You see that there is also a live stream, so you can subscribe to the channel and stay up to date with all of my video streaming and tutorials. Many of the tutorials that you can find already in my YouTube channel are in Spanish. So si eres de habla hispana, puedes encontrar un montón de cosas. But for the English-speaking persons, I am starting to upload all these webinar series. So you will find all of these webinars and tutorials online in this channel. So yeah, basically, let's jump to Grasshopper and start talking about loops in Grasshopper. So I'm going to switch sharing to screen actually, and I'm going also to take a look at what's happening in the chat window here. If there is someone that already wants to ask something, nope. So let's jump into Grasshopper. You know, maybe that, well, as Grasshopper users, I think that all of us sooner or later made this kind of rookie error, which is basically trying to create a loop in Grasshopper. For example, one stupid thing that comes to my mind: if I take a point container like this one and say set one point, set multiple points like this, and then I create a line between these two points. Oh, that's actually a polyline between these 2 points. And then, for example, I grab a point on curve and extract this one. So if I take this, for example, and say that I want to create a line starting also from this point here, you see that Grasshopper gives us this kind of error. The reason why it gives us this error is because basically the point on curve depends on the output of the polyline. And we are saying the polyline that its input vertex depends on its output, basically. So I always explain this to my students at university. It's like, I don't know if you are familiar with Back to the Future. It's like Martin McFly going back to the future and killing his father, basically. So loops are not possible in Grasshopper due to this kind of mechanism. Okay, so you cannot use the output of one function and throw it back and to the same function as an input. Okay, even if you do some kind of elaboration. So this is our problem today, and we are going to understand how to solve it. Of course, in order to solve this problem and to create loops in Grasshopper, you might want to go into the math toolbar and use some scripting. But we are not going to deal with scripting today. We are going to use a plugin, which is called Anemone. So Anemone is a very simple plugin. It has very few functions or components, call it as you want, which simply allow to create loops. So the basic behavior is to grab a loop start and a loop end. And these are the two main components that you might want to use. We are going to work only with these ones in order to create some loops. And I'm going to explain you how this work and what's the potential that you have already in this couple of simple functions. Okay. So the first thing that you might want to do when you grab these two components is close the loop. And in order to close the loop, you simply connect these two input and output. So this cable here is basically, this wire, this connection is basically closing the loop, because the loop in Grasshopper always flows left to right. But this wire here is sending back the data from the loop end to the loop start. Okay, so this is what happens. So the first thing you might want to do is this one. And as soon as you have it closed, you can start building the loop. Now, the loop asks for how many iterations or repetition you want to create. There is a trigger which basically fires the loop or makes it stop. And then there is the data that you want to put inside the loop. And you see that this is a dynamic component. If you zoom in, there is this plus here that appear, which means that you can also use several data flows inside of your loop. The only condition in this case is that if you increase the amount of data here, you see that everything becomes red, because it says that you also must have the same amount of data input here at the end. Okay, so if you want to work with more than one data stream, then you have to set things properly in both components. Okay, but I don't want to do this right now, so I'm going to get rid of this and refresh the script so everything goes back to normal. So repeat is basically how many iteration you want in your loop. So this basically is a numeric value. Okay, so I will set this between 1 and, I don't know, 100, like this. And there is the trigger. The trigger is needed to fire the loops, basically. So it is a Boolean value. Okay, so it is true, false. And I'm going to take a toggle. So I'm plugging this Normally what I do, this can be handled like independently from the loop end. You see that also the loop end has a trigger here, basically, which is, do you want to exit the loop or not? Normally, I connect this trigger here also to the exit. Okay, so it means, for example, that when this is set to true or false, it both starts the loop and make the loop flow until I want to stop it. Okay, so this is my usual standard setup for the loop. And then we go to data, to the data stream. So for example, data is basically whatever value, whatever the data type you want to put inside the loop. Now I'm going to work with a simple value, which is like 0. Okay, so it's a number. So if I put this value here inside the loop, you see that this is receiving this number, and it is also inputting the number inside the loop. Okay, and I'm going to do the simplest thing possible. I'm going to simply connect the data from the loop start to the data in the loop end. And then I close the loop, actually. So there is a data which is 0 flowing through the loop, getting to the loop end, and being sent back to the loop start. Okay. Then there is the counter, which is an important parameter. I'm going to plug here a panel in order to keep things under control. And this is simply a counter that will grow in time when we release the loop. Basically, if I set this to true, I am telling the loop I want to exit. Okay, so even if the true is triggering the loop start, it is also saying that we want to exit the loop. So with one click, we can stop the loop. And in the end, there is another output, which is data. Okay, so of course, in this case, I'm not doing any operation. There is a 0 entering the loop. Then there is the loop, the 0 flowing inside the loop, going back and forth. How many times, as many times as I define here with the repeat, and then coming out from the loop in the data, the output data of loop end. Okay, so if I decide, for example, that I want 10 iterations, and then fire the loop, you see that I get the counter increases up to 10. But I always get 0 here as a result, because this 0 is going back and forth between loop start and loop end without any additional operation. But if I take, for example, something like an addition and take the data value and add 1 to it, like this, and then send the result back to data, then in this case, we have 0 entering the loop, then 1 is added to 0, then we get 1 here. So loop end is receiving actually the number 1, and it sends it back to the loop start. And the loop start in the next iteration will not use 0 anymore. We'll use the value that is coming from the loop end. So we will have 1 flowing here, 1 is added, so it becomes 2, and so on. This receives 2, this will get 2, this will become 3, and so on. So if I now fire this loop, you see that I have 10 repetitions, and I get this output, which is increasing iterations after iteration. Okay. So let's do this with something which is a little more interesting. For example, let's see what we can do with a loop. So let's say I want to create a circle which changes in its radius over time. Okay, so the command that I want to use is basically this one. I don't care about the plane. I'm going to extract parameter and hide this container, so I get rid of the grid that appears here. And I want the radius to depend on from this loop. Okay, so what I want to do, I want to create a random number. If you watched the webinar from 2 days ago, it was about randomness in Grasshopper. Actually, I'm using this one so you can follow, but I do recommend that you take a look at the Heteroptera plugin because the way that randomness is handled by Heteroptera is way more efficient than standard Grasshopper randomness. And we will see this in the definition that I've prepared here at the bottom. But anyway, for now, this is more than enough. What I'm going to do, I'm going to define a range, which is basically the range of variation for this radius. So I'm going to set this with a construct domain, and I will set this between, let's say, 5.00 to, 500 as a domain start, and let's say 10.00. There is a chat message. The name of the random plugin, thanks. Yeah, of course. Let me write it down here. It's called Heteroptera. You can find it. You can find the tutorial on my YouTube channel already, and also on my website, because this is the webinar from 2 days ago. And let me. Yeah. Okay. So you have an idea of what it does. Yeah. This is. So we are defining here a domain between 5 and 10, and I want just one single number, okay? Now, you might know that if you take a panel and take a look at this value, if you are doing exactly what I am doing, you're getting the same value. So this is not exactly a random component, okay? It's a pseudo-random generator. What I'm going to do, I want this random value to change over time. So each iteration of this loop, I want this value to change. So the only thing that I can do, I wouldn't change the domain, because I want the domain to be, let's say, fixed between 5 and 10, which defines the radius, the range for the radius. But I want to change the seed, because the seed is what makes this random value change inside a given range. So if I connect here a slider between 0 and 10, you will see that if I change this, the corresponding random value is going to change. So what I can do, I need a changing value, which basically updates for each iteration of the loop. And this value, we already have it because it's the counter. So the counter is 0 when there is no iteration. It's 1 after the first iteration, 2, and so on. So if I take this and plug it into seed, what happens is that when I release the simulation, you will see that this number is changing. Well, it's quite quick, but I will increase this to 100, and you see that this number is changing. Because the counter changes iteration by iteration, and then the seed changes, and the random value inside the same domain is changing. So that's it. Basically, I can take the random value, plug it into the random, to the radius of the circle, and just release the simulation. And we have this circle like blinking like this. Now, if you take a look at the Heteroptera randomness webinar that I gave 2 days ago, you will understand also why you have this kind of flickering of the circle, which appears to be not so random, okay? But I will not go through this explanation here, yeah, you might also take a look at the other webinar and understand why this is happening. But anyway, this is already a loop which is giving some geometric results, some geometric output, okay? But of course, possibilities are basically infinite. So what I'm going to do, for example, next is start working with some kind of, let me group this. You see that, that in particular, in this case, I'm not using the values coming up from the loop end, because the loop end is still working with this addition here. So the loop end is just increasing from 0 to 101. Okay, so there is no use for this, but I am using only the counter. So this loop is basically useless in terms of this circle creation, because I'm just using a progressive value that simply increases between 0 and 100. Okay. So you can use the loop just to make this value increase over time and use it for any other application that you might want to create. Okay, but this is something that eventually we are not going to do for the next example. So I'm going to leave this here, so it won't disturb the rest of the simulation, the rest of the script. So this is the standard loop. Okay, let me organize things a little. And this is a first geometrical application depending on this useless loop, actually. So I'm going to control E, all of this. And I'm going to start from scratch also for you to see what is the standard workflow. So I do recommend that you familiarize with this. You take a loop start, you take a loop end, you close the loop first, then you take a toggle, connect this toggle to both trigger and exit if you want to stop the loop at the same time. Of course, this is a simple loop implementation. If you go into the Anemone toolbar, you will see that there are also other types of loops or other control for the loop, but this is the standard loop generation, okay? Number of repetition, I would set this between 1 and 100. Normally, I do recommend that when you create a loop and you set the repetitions to a certain value, initially you set the number of repetition to a very small value, because if the simulation, if the loop that you are creating involves, I don't know, lots of geometry, for example, or complex calculation, then in that case, in order to, you fire the loop and the loop starts running, and each iteration takes a long time to perform all the computation, then it becomes difficult to stop the loop. The Grasshopper starts to hang, and you are in trouble because you need to stop the simulation, the computer becomes unstable, and everything might crash, okay? So I do recommend that you set these to very small values and check if everything is working properly, okay? So for example, what I'm going to do right now, I'm going to create some iterations, some geometrical iterations. So for example, what I want to do is take a line, like for example, a generic line. So I'm going to set one line like this and feed this into the loop start. So what I want to do right now, I am taking this line and then I am shattering this curve here. I'm going to reparameterize it in order for this definition to work with any curve, not just lines. And I'm going to take as a parameter, I'm going to take a panel with 0.5. So I'm splitting this initial curve into two segments right now. And I'm going to feed the data input with this one. Now, you see that things here are starting to become quite complex. There is some data manipulation or data structures visible. You see that now we have data trees flowing through these wires. So let's take a look with a param viewer, what's happening. So you see that, yeah, we have this kind of nice data structure. There is a meme that I published some years ago, which is trees happen. So when you see something like this, you start to freak out. But yeah, it's quite normal. And you see that this tree, it gets more complex and complex iteration after iteration. So for example, if I set this to, I don't know, 10, you see that these two trees here are becoming like very extremely complex. Okay, now let's understand if we need this or we don't need this. You see how in this moment my Grasshopper has already become let's say very slow. Okay, I also use the profiler widget in order to understand what are the components or the functions that are giving us some problem or some, let's say, long calculation time. And I do recommend that you do this because this gives you an idea of what's happening in your definition. So I will decrease the amount of repetition just to have it, let's say, under control. You see that this doesn't update because my loop is still running. So this is set to false, which is exit false. Okay. So the loop is still running. If I decrease the number of repetition, I still get the amount of repetitions that I got previously. So I need to exit the loop and fire it again. Now, the question is, do I need this data tree structure or not? Let's see what happens here, because if I send a list of curves to this shader parameter here, each curve should be divided using the same parameter value. Okay, so eventually I don't need a list of a data tree of curves here in order for this shader to do its job. Okay, so eventually what I can do here, I can flatten this. Okay, so if I flatten this, I have 32 lines coming in and I have 64 lines coming out. They are in the form of a data tree, but even in this case, I don't need a data tree because soon after the data tree comes out from here, enters the data here, goes back to the loop start, and it's flattened. So what's the point of having here a data tree if I'm going to flatten it again? So I can also flatten this one and nothing changes because I have 64 lines as before. So in this case, I am avoiding a complex data structure and I'm going to have the same result. Now, what's the result in this case? There are 64 lines coming out from this loop end. I'm going to turn off the preview of everything here. I'm going to take a line container and see what I have here, 64 segments. So let's see what happens. Let's see how these segments are organized, because I was taking one single segment, shattering into two segments, and then I had one segment and another one. These two segments have been shattered into two segments. So it's like a fractal iteration, okay? So if I take, for example, a dispatch, let's see how these segments are organized. and I take a line container here. So I have these small segments here, and I also have these other small segments here. You see, very, very small segments. Now, let's decrease the amount of iteration. Let's switch it back to 1. Let's turn off let's untrigger the loop. And we have these two things. Okay, this is what comes out from the shader and the output of the loop end. So even if the loop is not running, the data are still flowing. Okay, so there is one line coming in, it's been shattered into 2 segments, and these 2 segments are coming out from the loop end and are dispatched using this dispatch component. In order to make it clear and don't have to maintain one of these components selected, what I'm going to do is use a custom preview with a color swatch like white and leave this to red. Okay. So if I make just 1 iteration, I get this. If I increase this, I have 3 iteration, 4 iteration, 5 iteration. You see that this is a fractal process, okay? And I can go on and on and on, because actually I'm not dealing with data trees, which makes things very heavy, just because of the indices involved in the data tree creation, okay? There is no need to have complex geometry in order to make data tree heavy. So in this case, having flattened everything, I don't have this kind of problem. And I also need to flatten the output, because even if I send here a list of curves, if I send a list, I will have a data tree as the output. Okay, so I need 2 flattens here. This is also something that you can learn from the other webinar, which is on data trees. But remember, I think it's fundamental to understand how data manipulation works. So here we have this nice behavior. Now, what I want to do, I don't want only the segment only to be split and split and split each iteration. Okay. So what I'm going to do, I'm also going to do another operation. So I'm going to reset the loop, and here we have the segments. Okay. So once we have the segments, what I want to do, I want to make a rotation, for example. So I want to rotate all these segments here. I want to rotate them using as the plane, which is basically the center point for rotation. I'm going to use something like the midpoint of this segment. So I'm going to grab another point on curve, which is the midpoint of these segments, and I'm going to use as rotation plane. You see that now they have been rotating like 90 degrees from their original orientation, because angle is set to 0.5 multiplied by p. But I want this angle to be variable, so I'm going to switch to degrees, and I'm going to use, for example, a slider between, I don't know, 0 degrees up to 90 degrees in order to have an extreme rotation, okay? Of course, if I have 0 degree and I plug this here, there is no change basically in the loop, because when I fire the loop, I still have the same result, because there is no rotation. But if I increase, for example, let me stop the loop, and let me set this angle to a small value, okay, like this. So each time that I run this loop, each iteration, the new segments will be rotated a little. So if I do this, you see that segments are being shattered, and they are also being rotated using this angle. Now, let's increase this in order to see some, well, 12 is too much. Let me, okay. 12 is too much. Let me stop to 10. So you have this kind of effect here, which is something like really a fractal geometry. Okay. So we only see basically the last version, because what we are doing here, data are being sent back and forth inside the loop. So when they come out from this data, we only have the final version, because this is basically, there is nothing in this moment, in this definition, which is recording the different statuses of this system as long as it basically changes over time. So what we can do, for example, is another thing. We can, well, there are several strategies that we can implement in this moment. One allows to keep under control the recording of the different phases of our system, and it is simply made with a data recorder that you simply plug here and use it to record the several iterations that come out from the loop end. So this is actually it is recording. I will get rid of the actual recording. So I'm emptying this recorder here, and I will fire the simulation once again. So you see that now we have trace of all the statuses, because we have the first two segments, we have which are the red one and the red one. Of course, now we have the dispatch. So the dispatch in this moment is useless. We only need to take a look at what happens here. We have the first two segments, and then we have four segments, and then we have 8 segments, and so on. Okay, so we are recording this data flow. If I increase this, of course, every time you let's say exit the loop, you have to empty the recorder. Okay. And if I increase this, for example, let's increase it to 15, and let's fire the loop. You see that now we get more and more segments. I think this 15 was quite extreme. You see that Grasshopper starts hanging a little. Let's hope it recovers. But you can see that there is something going on here at a very small scale. Okay, you can go deep and deep and deep, and you have this kind of fractal structure. Okay, so this is a way of recording the result of your loop. But there is also another way of recording the result of a loop, which is not data recorder. It's just telling the loop end that you want to record data. Okay, so if in case you do this and you plug a container here, you see that this one is becoming already very, very extremely slow because of the amount of iteration, and because this is a basically producing, let me double check, 65,536 line. Okay, because each segment is split by 2. It's progressive. It's a geometrical progression, so it becomes a huge amount of data very, very quick. So I'm going to decrease this back to 10, and I'm going to reset the loop in order for it to forget the previous version. And this is something that can be handled in a more light way. And you see that we get the same result, because actually we are not recording with a data recorder, but it's the loop end itself that's recording each iteration and sending it to the line container. Now, what happens is that we have the lines becoming smaller and smaller and smaller. So we have, it's difficult to look at the original, at the final fractal structure in this case. So what I'm going to do, I'm going to take this line coming inside the loop, and before shattering, what we can do is basically change its size. Okay, so we can also do it after the shattering, but it's just the same. I'm going to scale this geometry here coming out from the loop start. Take another. Let's get rid of this part here, and let's move this ahead. So I want these lines to be scaled around their midpoint, and I want them to be scaled like with a scale factor which is larger than 1 in order to make those lines bigger. So I'm going to scale up this fractal. And what we can do basically, well, actually, this is something that will not invert the trend. So lines are not going to get bigger and bigger and bigger repetition after repetition, but I'm going to scale up the whole structure. So if I scale this like twice the actual size, like this, and I plug this to the shatter component, I don't change the number of repetition, so I get this, and everything becomes more and more visible, but I don't have let's say, a clear understanding of what's happening, because I have a lot of lines being recorded. But anyway, this is something that is starting to become quite interesting and visible at a large scale. In order to take advantage of these iterations, what we can do, for example, is instead of working with this line, we can see if there is some more usable geometry that we can work with. For example, if we have these lines here, and also we must turn off the preview of everything that's inside the loop and before the loop. So we have these lines here as a result. We can eventually calculate the endpoints of these lines. So you see we have this nice point cloud here. They are all divided by lines. You see that the data here is being grafted Okay, each iteration is saved inside a different branch of the data tree. So for example, if we want to take a look at one single iteration, we can explode the tree. Sorry, we can explode tree. So we have first iteration is this one, second iteration, third iteration, fourth iteration, and so on. Okay, so you see that each iteration has memory of only one step, one repetition of our loop, and the amount of branches is exactly the same as the amount of repetitions that we set here at the beginning. Okay, so it's very easy to access each repetition individually with an explode tree. Okay. So for example, let's say we want to do this thing with one single iteration, which is the last one. Okay, so we have these endpoints coming only from the last iteration. Okay, and for example, here we have 2048 points. Here we have 2048 endpoints. And of course, if we take this points here and connect them with the endpoint, we get back to the same line. But if we connect all of the starting point with a polyline, for example, then we can start to have some kind of different result. We are connecting just the start point, and here we have, oops, sorry, and then here we have only the endpoint. Okay, so we can elaborate something based on the output of our loop. I will only leave the explode tree as future memory, so you will have it available. I'm going to share this definition in the description of the video as soon as it is published on YouTube. But anyway, we can do some operations on the output of the loop end, which is something that we are going to do with this definition here. So you see that basically with a loop, you are creating exactly the loop structure that you can create in any scripting environment. Now, Grasshopper is a visual scripting environment, so everything that you can do by writing some code, you can also do it in Grasshopper. Of course, it maybe eventually it takes more time and more complex structure than eventually creating a loop here, I don't know, using Python. But sometimes it's worth the effort because the result can be very interesting. Also, if you're not into coding, line coding, then you can create loops like this in Grasshopper using some plugins like this one. Also, you can create conditional statement like selecting different data streams and so on. But it's just knowing what sequence of functions you have to use. But in this case, this is basically what I wanted to show you with a geometrical operation. I'm going to trigger the loop, and I'm going to group and turn off everything here. So let's go to the definition that I have prepared here. I'm going to Control E. And let's take a look at what it does. So what it does initially is take this line. Let's analyze it step by step. Okay, so I have a line which is has a variable length. Okay, I can decide the length of this line, and take this line and sends the line inside this loop. Okay, now you see that this loop has two inputs, data input. There is a line, and there is also a numeric value, which is 5. Okay, so let's say that this is basically 6. Let's make it like 6, and this is 5. I have only 8 iterations, and the loop is stopped. What happens when I fire the loop? This is what happens. Okay, so I'm trying to generate some kind of trees, variable trees in Grasshopper. Which can be also useful for, I don't know, if you are into, I don't know, architectural visualization or something like that. You can also create your own, well, in this case, I am just creating the branches and of this tree. It's like, sounds like winter, but you can also create some scattering of leaves along this thing, and you can also give thickness to these branches and the trunk. As we will see later on, there is a quick scripting here that basically converts this into a solid mesh. But anyway, this is something that eventually, just to give you an idea on how you can use this Grasshopper to create some useful stuff. Of course, if I, for example, go at the end here, I have this line container which receives all the lines. I can bake it, yes, please. And I have this version here. And then I can just hit refresh the definition like F5, stop the loop, and fire it again. And you see I got a totally different tree from this definition. So let's bake it once again. Yes, please. And we have two different tree structures. So if you want to create random trees scattered on the surface for an exterior visualization, then you can also take these and have fun with this loop. But anyway, I'm going to go back here, reset the loop, and refresh the definition. What happens inside this definition? Well, what happens is very simple. It's basically the same thing that we just did with the previous loop. There is a line that gets inside the loop, and it's being splitted and split and split iterations after iteration. But splitting is not happening like with a shader. Okay, it's like I'm taking the original line, okay, which is this one, which measures 5, okay, and then there is from this point, from this original line, I take it, move it like on top of the first of the previous iteration, and then rotate this line twice with a rotation angle that I can control in order to create this ramification, this branching here. And then these two lines, the length of these two lines here depends on the numeric value that I am inputting inside the loop together with the original line. And also I have control over this angle here. Then there is the second iteration. This line is basically being displaced like this, and then it's being rotated like this. But there is also this other line, which is being displaced like this, and it's being rotated like this. So I'm creating a branching algorithm using simply a loop and some geometrical operation. Okay, this is what we are doing with this definition here. Let me grab this and take it here. Okay, so now, well, actually it's not 5, it has become 6, but you get the point. So I take the line coming out from data. So if I plug the line in data, it will be available in data, and it will go back inside here. Okay, and the numeric value, which is this 5, flows through D1, and must enter inside D1. So you see that D1, the data is just a subtraction where I take the initial value and subtract 0.25. This is basically defining how much we are shortening the branches each time we have some branching. Okay, so the next branch will be 6 minus 0.25, which is 5.75. The next branching will be 5.5. The next one, 5.25, and so on. We can decide how soon the branches die during this branching due to this value here. But you can also use any type of mathematical operation here. So if I increase this value, for example, my branches will become shorter faster. So if I take this and set it to 1 and fire the simulation once again, you see that the tree dies, well, actually the branches die sooner. Even if we have the same amount of branches, the branches are dying sooner because they become very, very short, okay? And if I, for example, set these to 0, there will be no shortening for the branches. And so this would become extremely long. Of course, there is also some other control because this is the main shortening. This is a control that defines the general shortening of our branches, but it's not only it. Okay, so let's go back to a more suitable value here. So we are back to this. Okay, what happens to the line? The line is being used to calculate the endpoints. Then these endpoints are being used to create a vector 2 point. There is a question here. Would it be possible to generate the same tree for a plan drawing? Of course, We will discuss this eventually at the end of this discussion. But yeah, it is possible. So you want to use it for some, so for some, planar view or technical drawing, right? So I totally get the point, because in 3D probably this, yeah, no problem. Because this type of objects here are, well, actually, if you're not creating a winter scene, it's basically useless. But anyway, yeah, you can do it. So what I'm doing here is taking the start endpoint and basically creating a vector 2-point, which is exactly the same length and the same direction and orientation of this line. So if I take a vector display, I want to visualize this vector. Actually, sorry, I want to visualize this vector in 0. So I take a point container, set 1 point, set 0, enter, and yeah, we have basically a vector that corresponds exactly to the original line. Okay. And once I have this vector, I'm going to rotate this vector using an axis of rotation, which is basically a random vector. Now, in order to create this random vector, you see that if I want to see this vector, yeah, this is the actual axis of rotation. This is what makes it possible to create a different tree each time that I repeat the loop. Okay, so it depends on this random vector. Because when I change, for example, the axis of rotation for this vector, what I define is basically, remember, we have the original vector, which is this one. It's being rotated using a random vector. So the rotation is creating these two directions here. Okay. And the axis is actually oriented like this. It's perpendicular to the plane in which this vector is rotating. So once I have these two new vectors, I use them to create an SDL line, starting from the endpoint of the original line and using these two vectors as the direction of the new branches. As for the length, you see that length here comes from directly from the D1. So if D1 is being basically shrinked as a value by 0.25 each iteration, then the length of this branch will decrease and decrease iteration after iteration. Now, let's see, for example, how we can create this random axis. Okay, there is some question. How can we add some thickness and radius to each branch? We will see it later on. So let's see how we can handle these axes here, which is basically the more interesting part of this script. Okay, which is basically this vector here. Okay, it's a small vector. I'm going to eventually scale it up with an amplitude in order to make it more visible. Let's set this to 5. Yeah, okay, so this is the rotation axis. You see that as this vector is oriented like this, the two branches are taking this orientation here, okay? But if I refresh the simulation, F5, you see that the vector changes and the branching happens in a different orientation. F5 once again, F5, 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 F5. So what I'm doing, I'm refreshing the simulation and you see that this vector changes randomly. So each time I hit F5, I get a new random tree from this loop. How is it possible? Because I am using this random number generator here from Grasshopper. They have a range between -1 and 1, all of them, but the Z, well, actually the Z component, because I don't want basically this vector to point downwards. Okay, that's the reason why I used 0 to 1. So basically, the vector that I am creating can be any vector in the upper region of the XYZ space, okay, on the Z positive region, because of these 0 to 1. And -1 to 1, -1 to 1 for the X and Y component means that if you see this from top view, you see that each refresh, this vector can change randomly in 360-degree around the Z axis, okay? That's why I placed here -1 to 1, -1 to 1. Now, we just saw that in order for these random values to change over time, we must provide a seed, okay? Now, what I did here was rely on a seed generator by Heteroptera plugin. So once again, do have a look at this plugin here. and do have a look at my previous webinar on randomness in Grasshopper. And this seed generator, what they are doing is basically generating these very high seed values, okay? Now, this is something that I explained in the previous webinar, but if I take a copy of this one, and you see that this is outputting 138, seed 744, and so on. If I plug this one, it is a different number. If I copy this one and plug it here, I get a different number, okay? So if I copy paste these three objects as I did here, I'm getting three different seeds, okay? I want these three different seeds to change each iteration. So I simply add the counter to each one of them. So this addition here is creating this seed plus the value of the counter. So I know that these seeds here are changing over time, each iteration of the loop. Okay, so this is what I'm doing. So as the seed changes according to a new random value, and it's being basically updated each iteration because I'm adding the counter value, then the seed is changing over time for each iteration of this loop. And it's also based on a seed generator that produces this kind of values here. So these values are not 0, 1, 2, 3, are very high value and very diverse values. So this makes it possible to get very random configuration of this vector. Okay, so that's how the basically the axis of rotation of this rotate vector is being created, and this makes it possible to have this kind of random branching, because each iteration, this vector is going to change, and therefore the branches are going to take a different direction. Okay, so if I, for example, get rid of, well, I'm not going to get rid of this. In case you want to study this definition, it might be useful to understand how it works. Just in this case, I do recommend that you hit F5 to refresh. Okay, so just if you want to study this, I'm going to turn it off, disable it. But F5 is basically recompute here in the solution. Okay, so you are basically refreshing your script, making all the calculation. So actually this definition is stopped. So I can take this and send it back to, for example, one iteration. Okay, so with let me refresh this, and also let's get rid of the preview. I do recommend that you turn off the preview of everything but the output when you work with this. Okay, so I'm exiting the loop, refreshing, and with only just one iteration, I get this thing here. Okay, if I reset the loop, hit F5, and run it again, I get different branching. Okay, so this is what happening due to this random vector that I'm generating with this small construction here. Okay, so if I increase this back to, let's say, 8 or 9 or whatever, I get branching and branching and branching. And you see, if you go up to, well, I wouldn't go more than 10, but if you go more than 10, you will get very, very nice trees for your, let's say, representation. So let me bake this because it came out quite nice. And as it is random, you cannot absolutely have no idea of how the result would look like after the loop. So this is nice, and I'm going to save it. Okay, so let me go back to 8 in order to have a lighter simulation like this one. Okay, if you don't hit F5, you always get the same tree. Okay, so if I do this, for example, I get this tree. If I don't hit F5, I get the same tree. You see, over and over. So the trick is hit F5 and then repeat the simulation. Hit F5 and repeat the simulation. Okay, you see that in this case, we get different distribution for the branches. Okay, yes, we can do this, for example, in 2 dimensions. Now, in order to make it in 2-dimensional, the only thing that you do is change the way you are creating this kind of geometry here. So let's do it very quickly. I'm going to take a circle, for example. The circle will have a radius, variable radius of 5, like this. Let me hide also this. Oh, well, actually, what I'm going to do, I'm going to do this new script like from scratch. So let me turn off these, and eventually in the end, we will see how to give thickness to this structure, okay? But for now, I'm going to create a circle, and I want to create a 2D representation for a tree. And so what I want to do, I want to, for example, evaluate this curve, reparameterize it, and evaluate it using, for example, well, I don't know, maybe, yeah, random values, a couple of random values like this. Range is set to 0 to 1, which is perfect. And then if I do this, I have these two random points here, okay? So if I repeat this, if I want to repeat this, it's better to understand what's the loop that you must create before creating the loop. Because if something goes wrong inside the loop, then Grasshopper might hang and you have to start from scratch, okay? So I prefer to create things manually and then understand. So the next step will be to scale the circle using the same center plane. In this case, it's useless because I'm working around the origin, but if you want to work wherever, you can simply set a point, for example, like set one point here, use it as center for this and center for the scale of this circle. And I want to scale it, let's say, with a variable value between 1. No, 1 will give us the same circle, so there will be no branching. So it would be like 1.1 and let's say 2, which is already a good scale factor, okay? So we have this variable step, and this is something that we will eventually change during the loop, because I want this step to eventually decrease and decrease and decrease to have smaller and smaller branches coming out, okay? And then we take this one here and repeat the evaluation, okay? We repeat the evaluation, we evaluate this not with the same values, we change the seed. For example, if I'm using a seed of, I don't know, like this, okay? For this thing here, I will eventually multiply this by 2 and use this for the second iteration, okay? And so therefore, in this case, what I will get is some kind of branching. Now, this is very important to perform this kind of operation because it gives you an idea if things will go wrong. So for example, what happens if I try to connect with a line, the center point with the two evaluated point here? So this might sound like good, okay? But once I have this, I also must do another thing, which is basically take these 2 points here, and I want to connect them as starting point with the new 2 endpoints here. And this is what's happening. So this is something that I don't want to happen, okay? So eventually, this thing here is not coming out right. So if you imagine this repetition after repetition, these branches here are going to be extremely variable inside this structure. So eventually, this is something that came to my mind because it would be the easiest way of creating this branching structure. But if you want to do this, you must take the first direction and use them in order to determine also the remaining, the rest of your branching. Now, this method is not leading us to an interesting result. So I prefer in this case to maybe make things more regular, okay? So for example, what does it mean? Let's reduce the randomness of the first step, okay? So for example, I have these two branching here. The first branching, I don't want it to be extremely variable, okay? I want to have this branching, the first branching, like under control. So it means, for example, that if I have this evaluate curve, I would eventually use a control value like 0.00 for the first point and 1 or 0.5 for the second point, more or less. I can change this manually. So if you want a different initial orientation, I prefer to change this not randomly because I want to keep this under control. So once we have the first branching, eventually you can create the first lines that are very useful in this case in order to have a more regular branching. So we have these, and we can repeat exactly the same structure. So we calculate the endpoints, and we create a vector 2 points between the start and end point. And then we decide, for example, how we want to use this vector 2 point. Eventually, I would start a new SDL line, for example, starting from the endpoint and using this vector. The length is going to be the initial radius minus something, like for example this minus, we were using 0.25, which is quite a good value for branching. And then we have this thing here, and I want this line here, I'm not going to use this, I want some branching occurring at this point. So what I'm going to do in this case is going to be easier, because I just need a simple rotation of this line coming out from these two lines here. I want to rotate them around there, the end point of this line, which was basically the start point of this SDL line, with an angle. And I'm going to use an angle, a couple of angles, which are basically set by a slider. Remember that we want to work with degrees. So I'm using an angle between, I don't know, something like 5 degrees, smaller than, let's say, I don't know, 45, okay? And I want this angle to be positive and also negative for the second rotation. So if I say 5, I am rotating counterclockwise, as you can see. Now I also need to use the negative angle. So what I want to do, I want to graft the lines, and I want to rotate them using these two angles here. And I also need to graph the rotation center. Okay, so if I hide the original line, I'm getting this branching, and this branching can be more open or more close. Okay, so let's say we work with some kind of intermediate value. And once we have this, we must take these 4 lines here, send them back to the endpoints, and repeat this loop. So if everything is set properly, what I need to do right now is take this. Okay, take this and the endpoints, copy paste it, because it will be the next iteration, and basically take this output geometry and plug it into curve. And you see that everything is starting to work fine. Okay, so once we have this thing set up and working, then we can start building the loop. So let's build the loop start and the loop end. Let's close the loop first. Let's take a toggle. In this case, for example, I do not recommend to use a false start toggle, because by default, we want this to be set to true, because we want to exit the loop by default, okay? So don't use the false start toggle in case you have it. And I want to create some iteration. We saw that more than 10 iterations becomes quite complex. So let's set this to 1 to 10. And let's give it a small value like 3. We saw that with 2 iterations, things works properly, but just to make sure, don't exaggerate with this value at first. So what do we want to pass to this loop? Well, actually, we can create, for example, you see that what we have repeated is from endpoint down. So endpoints are here. So the first step is our 2 lines. Okay, and I want to have these 2 lines under control, so I will leave them outside from the loop. Okay, so I'm going to take this line and pass it to the data input. And then I'm going to take all of this thing here, place it here, move the loop away. So the line here is connected to curve, but I want this data here to be connected to curve in order to calculate the endpoints for each iteration. Okay, so this connection here is basically substituting this connection here. Okay, so basically I want to get rid of this part, and I have my first branching coming out from this, and I want these lines to go back to the loop start like this. Okay, and let's refresh it, and let's see what happens if we fire this. Okay, so you see that it's working properly. Okay, now the reason why you lose the intermediate branches is because we are not recording data here. So if I record and fire this, I will have all the branches, let's say, saved inside the loop end. Okay, now once you have this, you can play with it and change the parameters and implement whatever type of data of geometric structure you want to create. Okay, you can also work with several more lines for if you want. For example, if I use, I don't know, another slider here, and I have this thing. Each one is creating a different branch. Okay. Um, so another thing that you might want to do, for example, is we are providing here just two angles, which are basically affecting each of these lines. But eventually we can try also with, instead of having one angle and the opposite of this angle, we can work with one positive value and one negative value for an asymmetrical branching. Okay, so this is basically what's producing this kind of extremely symmetrical structure. Okay, because the angle is the same, it's just opposite from each other. But yeah, you can basically play with this definition and have your planar view of a tree ready for your AutoCAD plans. I do recommend that you work with Rhino, by the way. So yeah, this is pretty it. Let's go back to our previous definition before ending the webinar. Thanks. You're welcome, Tiziana. Okay, so let's get back to this, and I'm going to show you, for example, how to give some volume to this structure, even if this is not the topic for this webinar. So let's take a look at this. Let's say we have this, well, I'm going to simplify things a little because I don't want to waste a lot of time in this mesh creation. But yeah, let's say we have this simpler structure, okay? So the lines are here. What I'm going to do here is basically organize this set of lines in the proper way, which means basically having the branches grouped by length. Now, if you don't understand what I'm doing here, I strongly encourage you to take a look at the data trees webinar. Okay, so just take a look at that webinar in order to understand what I'm doing here, because it's quite important. But here we have the same lines, but they are grouped by length. Okay, so as I have them grouped by length, what I want to do is, because I know that the length of this line is decreasing along the branches. So what I want to do, I want to give a thickness which is bigger at the base of the tree and smaller at the tip of the branches. Okay, so that's why I'm grouping the lines by their length. Okay, so here I'm using a plugin, a Grasshopper plugin, which is called Dendro. Dendro basically it's the alternative version that I am using right now. First, I was using Cocoon, but Dendro, I find that Dendro is a little faster than Cocoon. Okay, but if you want, you can still play with Cocoon. It's still valid. But Dendro is this one. Okay, so what I did here was take the lines coming from the branch, exploded the tree. Okay, so you see that here we have these branches here represent the length of the lines converted into an integer. Of course, these lines do not measure 4, 5, or 6. They have some kind of decimal values. Okay, so if I okay, let me get rid of these and these and these. Okay, so we have these lines coming out from our tree, and what I do here, I use Dendro to give them a specific thickness using these radiuses here. Okay, so you see there is an increasing radius. This is not actually receiving nothing because I changed the shape of my tree. So each time you change the shape of the tree, as this Dendro cannot be actually, yeah, it could, but I didn't do this for this webinar. You can basically connect parametrically this mesh generation to the branches that you are creating in your loop. Okay, so we have a variable number of loops of repetitions, so a variable number of branches, and also we have a variable length due to this value here. So you don't always get the same data tree structure, basically. And so what happens here when I let's turn off the lines. What happened with Dendro is that we get this kind of object here. Now, I'm not going to play with Dendro too much in this case, but you see that if I go back to my values, you see that with these, I am only affecting the upper branches, okay, as you can see, while with these, I'm affecting only the base of the tree. So if you have the proper data structure in your coming out from the loop, and you set Dendro to work with any branching level, then you can create some nice tree structure, a three-dimensional tree structure. There are also some smoothing component for Dendro. I'm not going in details with this, but yes, you can play with Dendro in order to have this kind of three-dimensional aspect for your tree. And also, I do recommend that you split your workflow using a data dam, for example, because it's not safe to have Dendro calculating in real time the new version of the data tree that you are creating with the loop. I mean, if I don't interrupt this data stream here, Dendro will receive dynamically the iteration after iteration, a new set of lines. So it will be calculating in real time, and this mesh generation here is not so simple. Okay, so I wouldn't recommend that you use the same data stream. Just place a data dam or physically interrupt this the flow here, and then just hit play when you're ready with the new version of your data tree. So if I, for example, stop the loop, hit F5, run the loop again, and just hit play here, I get a different tree, okay, in 3 dimensions, of course. But anyway, this is something that you might want to play with in your spare time. Was there any question here? Yes, there is also another plugin, which is Fatten. Yeah, there is another plugin which is called Fatten, but actually there are several plugins that you might want to use for this let's say mesh creation or NURBS creation as you prefer. Okay. Let me also double check if there is any question from the YouTube. Oh, okay. It's possible for me to install this plugin. No version 0.0.0.0 is running my running 0. Oh, okay. Some compatibility probably. You can convert this into something like a column or mushroom structure. Yeah, well, in case of architectural application, for example, for columns, I wouldn't recommend that you use this branching algorithm because it has no structural meaning. Okay, it's just splitting a structure into branches, but without any structural meaning. Okay, mushroom structure, yes, you can. You can simply tweak the parameter inside the loop, and you will get a nice umbrella style or mushroom style branching. What is the keyboard shortcut for disable object and also group in same time? Well, actually, Control plus G is for grouping, and Control plus E is for enable disable. Actually, it is not one single step. I'm doing it with 2 different hitting. Okay, so Control G, Control E is not one single time. Another question here from the chat. Oh, Ariel, nice to have you here. Okay. You don't have access to last Kangaroo recorded because we still have to upload it. Okay. So later on today, you will have the last session for the origami available on YouTube. Yeah, you're welcome. Okay, guys, so that's it for today. I hope you enjoyed the webinar, and let's stay in touch. If you have some doubts or whatever, I do recommend that you subscribe to my YouTube channel and also activate notifications, because that's the way you will receive new webinar announcement. See you tomorrow, yeah, for the NURBS topology. So yeah, I hope to see you tomorrow. If you didn't make it on time to register for the NURBS webinar, remember that it will be streamed on YouTube as well. So don't miss it because it's going to be extremely useful for those who work with Rhino. So have a nice day, evening, night, guys. See you. Bye.